Good morning, everyone. Today I want to share something that sits at the fascinating intersection of chemistry, physics, and believe it or not, a very pleasant Mediterranean evening. When you add water to ouzo, something remarkable happens. The clear liquid instantly turns milky white. This isn't just a party trick. It's a window into one of the most elegant phenomena in soft matter physics. Over the next few minutes, we're going to unpack exactly what's happening inside that glass. Here's how we'll structure our journey. We'll start with the spectacle itself, what you actually see when water meets ouzo. Then we'll dive into the chemistry, the three-component system that makes this possible. After that, the real physics, nucleation, metastability, and why these droplets refuse to disappear. We'll trace the story from ancient Greek stills to cutting-edge nanoscience, and finally explore why any of this matters beyond the taverna. Let's begin where every great scientific story begins, with observation. What actually happens when you pour water into a glass of ouzo? The answer is deceptively simple to describe, but the physics behind it has only recently been understood. Here's the spectacle. Ouzo is clear when it's poured neat, but the moment you add water, typically 3 to 5 volumes of water to 1 volume of ouzo, it transforms almost instantly from transparent to a dense, milky white. The key insight is that this requires no shaking, no stirring, and no added chemicals. The oil, transanethol, suddenly nucleates into billions of microscopic droplets that scatter light in all directions. That's what your eye perceives as cloudy. Let me emphasize, this happens entirely on its own. Nature is doing the work for free. To understand why this happens, we need to look at what ouzo actually is. It's a three-component mixture. First, ethanol at roughly 45% by volume, that's the solvent. Second, water at about 55%. And third, this is the crucial ingredient, transanethol, the essential oil extracted from anise seeds, present at just 0.1 to 0.2%. When ouzo sits in the bottle, the high ethanol concentration keeps the oil perfectly dissolved. But when you add water, you're diluting the ethanol. Suddenly, the solvent isn't strong enough to hold the oil in solution anymore. The oil has to go somewhere, and it does spectacularly. Now let's get into the physics. This is where the Ouzo effect becomes genuinely fascinating from a scientific standpoint, and where it reveals principles that extend far beyond a Mediterranean aperitif. The key to understanding the Ouzo effect lies in the phase diagram of this ternary system. When you add water to ouzo, the composition doesn't follow a straight line through phase space. It follows a curved, nonlinear trajectory. At a certain point, that trajectory crosses into what's called the metastable zone, or more specifically, the ouzo domain. In this narrow composition window, the oil is supersaturated. It wants to come out of solution, but it's temporarily trapped. What happens next is spontaneous nucleation. The oil molecules cluster into droplets all at once, with no external energy input. Within the ouzo domain, the mechanism is homogeneous nucleation. The oil molecules, now supersaturated, spontaneously aggregate into tiny clusters that grow into stable droplets. This is distinct from what happens if you add too much water too quickly. At that point, you cross the boundary into spinodal decomposition, which produces a much less controlled result. The ouzo domain is narrow, but it's reliably accessible through the simple act of pouring water into the spirit. That reproducibility is what makes this phenomenon so valuable to study. Now, here's a number that I think really captures the elegance of this process. The droplets that form are between 50 and 300 nanometers in diameter. To put that in perspective, a human hair is roughly 70,000 nanometers wide. These droplets are about 1,000 times smaller than that. And they're not just small, they're remarkably uniform. The size distribution is narrow and unimodal, meaning almost every droplet is roughly the same size. For a process that happens spontaneously with no surfactant and no mixing, that level of uniformity is genuinely extraordinary. Perhaps even more surprising than the formation is the stability. Normally, if you create an emulsion without a surfactant, the droplets coalesce and the two phases separate within seconds or minutes. But Ouzo effect droplets persist. Why? Because in the ouzo domain, Ostwald ripening, the process where larger droplets grow at the expense of smaller ones, is negligible. The Laplace pressure difference between the largest and smallest droplets stays below 100 pascals, which is tiny. The droplets simply have no thermodynamic driving force to coarsen. They stay suspended, sometimes for days. The science is elegant, but the story of how we came to understand it is equally fascinating. Let's trace that journey, from ancient alchemy to the modern laboratory. Distillation itself has ancient roots in Greece. Early alchemists and physicians were extracting essences through heat and steam long before anyone called it chemistry. By the 19th century, ouzo production was flourishing, particularly on the island of Lesbos, which remains the spiritual home of the drink to this day. But the scientific naming had to wait until 2003, when Stephen Vitale and Joshua Katz published their seminal paper and formally coined the term Ouzo Effect. Fast forward to 2023, and researchers achieved the first direct nanoscale imaging of the droplet formation process. Then, in 2025, mathematicians at Loughborough University published a new model explaining the long-term stability, closing a major gap in our understanding. What started as a folk observation has become a rich field of modern research. We have explored the science and the history. Now let us step beyond the glass. The ouzo effect is not just a curious party trick. It has become a powerful tool across multiple industries. What makes it so valuable is that it achieves emulsification without any surfactant. No added chemicals, just the physics of spontaneous nucleation. This means cleaner, simpler, and often safer formulations in fields where purity is paramount. Let me walk you through the key application areas where this phenomenon is already making an impact. The pharmaceutical industry was one of the first to recognize the potential here. Drug molecules that are poorly soluble in water can be encapsulated in ouzo effect nanodroplets, enabling targeted delivery without the toxic surfactants that would otherwise be required. In food science, the same principle allows manufacturers to create stable nanoemulsions for flavors, vitamins, and nutraceuticals, all with clean label appeal that consumers increasingly demand. Cosmetics companies are now adopting surfactant-free emulsification to produce creams and lotions with exceptionally uniform texture and longer shelf stability. And in materials science, researchers are using the ouzo effect as a templating method to create precisely structured polymers and porous materials with controlled architecture. Each of these applications flows directly from the fundamental physics we discussed: spontaneous nucleation, narrow size distribution, and remarkable stability. Let me bring everything together with 4 key takeaways. First, the ouzo effect is fundamentally about spontaneous order. When conditions are right, nature organizes oil molecules into remarkably uniform droplets without any external energy input, producing particles in the 50 to 300 nanometer range. Second, this happens when a ternary mixture of oil, a water-miscible solvent, and water crosses a specific compositional boundary into the metastable ouzo domain, a path you can trace on a phase diagram. Third, we have seen how industries from pharma to food to materials are already harnessing this phenomenon for cleaner, simpler formulations. And finally, this is very much a living field. Teams across Europe, including a major CNRS collaboration in France, are using microfluidics and large-scale numerical simulations to push our understanding further. The next time you see a glass of ouzo turn white, remember, you are watching thermodynamics orchestrate order from disorder right before your eyes.